So I have a feeling that you guys have done composite functions. If not, no worries, we'll teach it like you haven't. And you might not know from that name, but when I start showing you, I think you'll probably recognize it. But only at a little limited amount. But I don't know that you've done inverse functions. Now, neither of these are overly complex. There's some algebra involved, but you guys daily are getting better with your algebra. But I just want to walk you through these. But before we get started, I want to talk about what a composite function is really doing, because I've had people in the past that are like, okay, I know the math, but what the heck am I doing? Okay, so for instance, do you guys understand that there are equations to convert from like Celsius to Fahrenheit and Fahrenheit to Celsius?
Yes.
And you know that there are equations that convert from like Celsius to Kelvin. Do you know what a Kelvin temperature is? Okay, so a Kelvin temperature simply is 273 degrees more than Celsius. All right? So if I gave you a Fahrenheit temperature, like 55 degrees, to be able to get to Kelvin, you would first have to convert Fahrenheit to Celsius, maybe through this formula, right? Plug it in there, do the math, get your Celsius. And then you'd have to use the Celsius formula and add 273 to it to get to Kelvin. And it'd be a two-step process, right? Are y'all with me? Now, in your everyday life, so a two-step process, by the way, doesn't have to be a two-step process. A two-step, there's probably an equation that you could just plug in and a Fahrenheit, and it just spits out a Kelvin. And you don't have to go through two steps. And that is a composite function. Okay? So if there was an equation, which we're about to find, that actually does that, and this one does, and I'll show you this process, you could just say, hey, plug the 55 in right there, boom, it spits out the Kelvin. And that's what a composite function does. Now, in this case, it's not worth memorizing another function, because it's so easy, if you remember Kelvin or done anything with it, that it's just 273 more than that. So most people would just still plug in Fahrenheit, get their Celsius answer, tack on a 273. And that's fine. It's kind of like going to the store. Like if I go and I buy a bunch of clothes, there's two functions that are in question. Like let's just say I buy 5 pairs of socks, and each pair of socks is $7.50. So there's a function that says, hey, 5 times, or what f of x is $7.50 times the number, right? And you plug in a 5 and it gives you the cost of the socks. But I can't just walk out with 5 pairs of socks before I pay tax. So that's another function that says, hey, take that and then multiply, what is it, Homewood, 9%?
Yes.
Down Birmingham's 10? Brutal. Like some states don't even have sales tax on food, things like Arizona, there's no sales tax on food at all. And then other taxes like 4%. They hit you harder on property taxes, and they hit you harder on other things. But like our tax rates, if you're poor and you're paying 9% tax on stuff, that's brutal. You ought to probably give people a little break on that and then hit them on property or other things. But that's my opinion, whatever. But the point is, that's a composite function because there's two things. There's a function calculating the price of the socks and another function calculating the actual tax. And then you add them together, right? I could put those together into one function. And that's what the computer does, right? I mean, it actually spits out totals and then puts the tax on there. But that result is a composite function. Are y'all tracking with me? So all a composite function does is take two different things that are going to be acting on each other, and it puts them together. Okay? So to actually do a composite function, you have to know what the two functions are. So this is an example of a Kelvin function. If you know the Celsius, you plug it in at 273. So if you know the Celsius you want to work with, you plug it in, add 273, and it gives you the Kelvin at that Celsius temperature. Right? And this is a Celsius temperature. If you know the Fahrenheit temperature, right? If I want to find the Celsius at 20 degrees Fahrenheit, I plug 20 degrees Fahrenheit in there, and it gives me the Celsius there. But for a composite function, it says, if I want to find K of C of F, okay, it says, take the C of F equation, which is that, and plug it into the Kelvin equation. So I'm going to take the whole C of F. It's kind of like a substitution. I want to take the whole C of F, there's C, I'm going to plug that in for that, and I get it plus 273. And sometimes you have to plug it in more than once if there's more than one C. And most of the time it doesn't look this ugly too. They're like, you actually see like f of x and g of x and stuff like that. It looks a little more normal. And then when you simplify it, you get a new function that allows you to go straight from here to there without going through both formulas. That's all a composite function is. Now, I'm not gonna probably mention this again, and in the future, you're probably not even gonna be thinking this way, but that's what it's doing. And you do it all the time, maybe not all the time, but you do it a lot in your everyday life, and in finances and paying stuff, you just don't think about it. It's just kind of what happens. Think about it. You go to buy food at a restaurant, and then there's the function for the food, there's a function for the tax, and then there's an extra added on function for a tip. I mean, there's all kinds of things that are going on that you're not really thinking about mathematically, but that are happening. All right? So let me just show you mathematically what it looks like, a lot more sterile looking and not quite as complicated. So I have two functions here, f and g. So let's just say that one was a function converting from something to something, and then another one was converting that from something to something else. The composite of g of f of x is just a big substitution. So this is saying, like, for instance, if I would have just asked you for g of 2, what would you have done with that 2? Plugged it in for x. What if I said g of 20? What would you have done?
20.
Plug in 20 for x and simplify. What if it said g of happy face? What would you have done?
2 happy face minus 5.
2 happy face minus 5. What if I say g of f of x? What should you have done?
2
Plug in the f of x. Except instead of writing that, I plug in what f of x would be. So instead of writing this, I'm going to plug in what f of x is,
x squared minus
and then subtract the 5. Are you seeing that? So a g of f of x means take the f of x, which is that, and plug it everywhere x would occur in the g function. There, and then minus 5. And then, of course, you got to clean it up. So for me, this is my answer to this, minus all this other junk right here. So for me here, if I'm doing g of f of x, I take the f of x function, I plug it in there, and I get this, and then I just clean it up. 2x squared minus 6x plus 2 minus 5 is a negative 3. And guys, this is the new function. Anybody right now tempted to set this equal to 0 and solve? Because on my test, every year I have like 5 or 6 people that set that equal to 0 and solve. We don't want to do that. Because we were trying to find what? A new function. And that's my new function. And the new function allows me to go straight, like if instead of going through f and then to g, it allows me to go straight from the x all the way to the y of the last one real quickly. Now this is what I do when I want the function. All right? What do I do if I just want g of f at 6? Now, the hard way would be to actually find the function like I just did. And this is, I'm saying, if all I did was ask you this, and this I think you've done in like Tyrese class, but the hard way would be to actually find the function and then plug in 6. And watch, I can do that by just plugging the 6 in and simplifying. That's 36 times 2 is 72, minus 36 minus 3 is 33. I haven't made a mistake. But without finding the function, you could just go through f first. What is f of 6? 36 minus 18 is 18, plus 1 is 19. So if f of 6 is 19, I can replace the f of 6 with a 19, drop the g down. Now, what do I have left? G of 19. G of 19 says plug 19 in that. That's 2 times 19 minus 5, which is 38 minus 5, which is 33. So what does that mean? G of f of 6 is 33. And in this case, I didn't have to actually find the function because all I needed was the value, but you can see it gives you the same thing. So doing it this way, this would be like me finding the Celsius temperature, and I did, and then plugging it back in and finding the Kelvin temperature, and I did. I went one function at a time. This, I went straight from Fahrenheit to Kelvin. Are you seeing the analogy there, the comparison? So I think finding the composite function first is probably a waste of time in this case. I would never have done that, but since it did ask for it, great. Now, if I say g of f of x, you'll notice I put the f of x function into the g. What do I do if it's f of g of x? I take the g of x function and I plug it into the f. So in this case, I would take the 2x minus 5 and plug it where?
X squared and 3.
So in there and in there. So that would give me the g of x actually goes in there and there. So here's my g of x, 2x minus 5. And sadly, what are you going to have to do with this? You going to factor it? No, because I'm simplifying, right? There's no f for factor and simplify. You just clean it all up. So square the first, that times 2, square the last, distribute some junk, and then 4x squared minus 26x plus what, 31, 41? And do I try to factor that? No, because this is my new function that allows me to go straight from plugging a 6 in to the final answer. But if I wanted to find f of g of 6 and I had that function, great. It allows me to go straight there. So look at the math. I get what? 36 times 4, which is 144. I get 26 times 6, which is what? 156. Plus 41, which is a what? 29 maybe? If I haven't done bad math. But look, here it's probably even easier. What's g of 6? 12 minus 5 is 7. So I'm going to replace the g of 6 with what it's equal to. And then what's f of 7? 49 minus 21 is 28, plus 1 is 29. So if that simplifies to that, and that's 29, then f of g of 6 is 29. And it's probably a little...
Thomas Reed's.
Oh, awesome. It's probably a little bit more simple, please.
It's crazy.
Like in like a hazmat lab or whatever. No germs. Are y'all with me on this? So these are composite functions. And in AP Calculus, you'll be much further along in 2 years, and we'll be applying some of this composite inverse stuff literally today. In AP Cal, we're doing some of that stuff. And I had to kind of dig out some of their brain out of mothballs because they're like, whoa, what does that mean again? But hopefully we're in good shape. Y'all remember doing any of this?
Yes.
Did you do it with functions as well?
Yes, we
So I know you did that kind of stuff, but if you did it with functions, great. If you don't remember it, well, definitely get some practice tonight. All right, so a couple other things I want to talk about, and this is all a prelude to logarithms, which we are going to really begin, I believe, on Monday. All right, but Monday, there's a reason why I'm covering this. Well, for a lot of you, you're going to go, big deal, I don't really need to know this stuff, but I wanted you to see the relationship, and this is why we need to talk about inverses and then composites. So right here, we just saw from the problem we just did that g of f of something was not the same thing as f of g of something, right? Because literally we just did g of f of 6 and f of g of 6, and we got two different numbers. And we also had two different functions, didn't we? But occasionally, g of f of x and f of g of x are equal. And when g of f of x and f of g of x are equal, that means that they also, what you plug into the f and get an answer for, and then plug that answer into the g and get an answer for, is the same thing you began with. And when that happens, there's something special about these two functions. All right? And what that means is they are inverses of each other. Now, inverses may mean nothing to you right now, but that's what we're going to start. But the definition is important. In fact, today in calculus class, you will see, I'll show you. In calculus, the very beginning of this whole lesson began with the notion of a function and its inverse. When you make a composite function, you begin and end what you start with. And then the whole proof we did for this derivative of an inverse function was based on that. Okay, so this kind of stuff doesn't go away. We're kind of planting seeds right now, so that in the future when we see this stuff, we won't be surprised by it. Are you with me? So if all that looks really nasty, it probably should. but you'll be shocked how much further you'll go from right now and 2 years from now. It'll be like, it's just night and day. Even by the end of the year, it'll be night and day what you know and your abilities. Because you really do progress a ton in 10th grade through this class and as well as next year. Okay? So anyway, what I'm basically saying here is, if they're inverses of each other, there's some properties that come into play. Okay? And also, this little -1, it's really annoying that they did this. You'd think that they'd put an I up there for inverse or whatever. But -1, we just talked about -1 being a what?
1 over.
A 1 over f. It does not mean that when we're talking about functions. So like if I say f -1 of x, we're talking about a function that's over here, some function it's equal to. Don't go, oh, that's the same thing as 1 over f of x. Don't do that. Okay? And you'll see that with inverse trig functions. Like you'll learn about sine of x. Well, there's also something called inverse sine of x. And it's not to be confused with the reciprocal of sine. If you look at that and say, oh, that's the same thing as the reciprocal, that's not true. That is cosecant of x. You might remember that from geometry or whatever, but you can't confuse it. So don't look at a -1 when you're talking about a function and ever think that it means reciprocal. And I gotta be honest, it's just maybe take a little time for that to kind of, you to get comfortable with that. With trig stuff, a lot of times books will avoid that inverse, and there's another way to write inverse. It's called arc sine or arc tan or whatever. They use the word arc, means the same thing, and we'll get to that later on in the year too. But just be aware of that this f -1 doesn't mean flip it. Because it's very easy to go, oh, but if I flip it, it puts it on the bottom, and then I could cancel, and I don't know, or even worse, if I flip it, it puts the f on the bottom, and then the f's cancel, and then it's true. That logic might mathematically look true, but that's not good truth. Are y'all with me? So don't do weird stuff like this when you see that -1. All right? So, moving on. Okay, so right here I'm going to talk about these inverses a little bit. But the big thing I want you to know about inverses is this. If you have a function and its inverse, okay, any point that shows up on the function on its inverse, x's and y's are flipped. So you can look over here and say, look, I have two functions that happen to be inverses of each other. Just trust me. Any point on this function, if I flip the x's and y's, it becomes a point on this one. And you can see that over and over and over. Are you with me? So that's the main issue when you're talking about functions. Now, what does that mean when you graph these functions? Check it out. I just graphed both of these functions. There's the function, and there's the inverse. And they kind of look like they're reciprocals of each other. Are you with me? And they're reciprocals of each other, not along the y-axis, not along the x-axis, but at the, what? Y equals x-axis. And why is that? Because a y of this one is an x of that one. So points like -2, 0 over here are going to exist as what? 0, -2 over here. Points like -1, 1 point, I'm guessing, 75 here are going to exist as 1.75, -1. So if I ever ask you, and all I do is give you the f function, and I say, hey, there's the f function, sketch the derivative. Really, all you have to do is find enough points on this f. Just find a bunch of them. I always use the beginning and ending, any whole number looking values that I can find. Definitely intercepts, because those are pretty easy. And I find a bunch of them, and if I find this coordinate is like 2, 4, then I graph 4, 2. If I see that this one is 2.3 up 5, I graph over 5 up 2.3. If I see this is 1, 2.2, 2.2 up 1. And if I do that for enough of these, I get enough points plotted that I can just come in here and sketch. Does that make sense? Now sometimes I have people that go, well, am artistically inclined. So they will see something like, I'll give you some examples. They'll see something like this function and they'll go, if it's a mirror image, I'm just going to sketch this mirror image. And they come in here and they're like, they always get a really good start. And then I start seeing this. They just kind of lose it. And it started out as a mirror image, and then all of a sudden it was like went bizarre, didn't it? And clearly that's not a mirror image. And if you're like, I can't see that it's not, then you're probably not the person that needs to do a mirror image. But if I plot enough points, right? If I go, all right, that point right there was 7, 6, so let me mark 6, 7. And this point right here was 3, 5, so let me mark 5, 3. And this 0, 4, 4, 0. Negative 1, 2, 2, negative 1. Negative 2, 0, 0, negative 2. Negative 4, negative 1. Negative 1, negative 4. Negative 7, negative 1.5. Negative 1.5, negative 7. At this point, it's going to be fairly hard for you to not sketch this good enough. And even if it's not perfect, it's good enough. Now don't just mark 3 points. I mean, put enough in there that you really get some help on this. And the more you have, the better it's going to look. Right? Y'all with me? What about this one? F of x equals 2x minus 5. Y'all know what that looks like?
Just plug it in.
It's a line that has a y-intercept of negative 5 and a slope of 2. So it would look like this. So based on that, could you sketch the derivative? I'm sorry, can you sketch the inverse?
Would you inverse or find the x-intercept and
I'm going to find anything I can and then switch the coordinates. So which points do you know? I know 6, 7, so 7, 6. I know 5, 5, so 5, 5. I know 4, 3, so 3, 4. I know 3, 1, so 1, 3. I know 2, negative 1, negative 1, 2. And at some point I go, oh wait, these are both lines. That means this is going to have a similar relationship. But they look like mirror images, don't they? Now I want to show you something here. And this is the key to actually finding what this inverse is. Can y'all tell me what the equation of this inverse is?
1/2.
Slope of a half, x,
Plus 2.5.
plus 2.5. So that's the equation. Now you might not say that with a ton of confidence, but right here with the slopes, if I'm going up 1 over 2, then it makes sense I can go up 1/2 over 1. Simple proportions and geometry, right? Now let me show you how I can also get this, and this is the key to finding inverses when I can't see that from a picture. Because I'm guessing right here on this maroon graph or whatever, you can't tell me what the equation of that is, can you?
no.
Yeah, I can't either from just eyeballing it.
Yeah, GW could.
Maybe. Let's see. Okay, so here we go. If you have a function, like in this case I have 2x minus 5, and I want to find an inverse, all I have to do, remember the whole thing, we said that so far all we've been doing is taking x values and y values and doing what? Switching them. Well, I've been doing that what we call discretely, which means for individual points. What if I did that non-discretely, okay, which means do it for every x and y value? Isn't this a y right here? Doesn't that mean y? And doesn't that mean x? What if I just switched these x and y's? And then, so it would be pretty, resolve for y. What do you get when you resolve for y now? Add the 5 and divide by 2, and I get y equals 1/2 x plus 5 halves. So the inverse of f of x is 1/2 x plus 5 halves. And I can do that here. If I know that function, I can find the inverse, just like I found it discretely by switching every x and y coordinate. I could find it over the whole domain and range of this by just switching x and y here. And by the way, I'm not really switching just two of them. I'm really replacing every y with an x and every x with a y. So if there was more than one x, all of those x's would become y's. That would be harder to solve, but you probably won't run into that in algebra 2. You definitely won't run into that in algebra 2. Are you with me so far? Okay, so you're going to see all kinds of questions about this kind of stuff moving forward. So let's just see. Right here, if I gave you this function, f of x equals 2x cubed minus 1, can you, based on what you now know, find the inverse of f? So what would you do? You're going to replace that with what? That is y. So if that's y, you replace that f of x, which is y, with x, and that x with a y. Does that make sense? Remember, f of x together, that whole thing means y. So replace the f of x, which is y, with an x, replace the x with a y, and then what do you do to make it pretty? Solve for y. And by the way, that is the inverse right here, it's just not pretty. We want to literally make it pretty. So I'm going to add 1, then what? Divide by 2, then what? Cube root. So I'm going to cube root both sides. And I'm going to give you a little bit of a break. So right now the cube roots go away on the right, and I get y equals this, but we want to write it like a inverse function. So I'm going to go inverse function of f of x to replace that y equals the cube root of x plus 1 over the 2. Now, some of you are going to look at that and go, do I need to rationalize the 2? Technically, yes. I probably wouldn't count it wrong on this test if you had that, because we're doing a lot of this stuff for calculus, and calculus we don't care about rationalizing. But if you were to rationalize it, it's better. What would you do?
You would multiply.
I'd rationalize, yeah, but I don't use just a root. A lot of you on your test did 2 2's here and there. But if it's a cube root, I need 3 2's down there, right? And I already have 1, so I need to use 2 more, so 4 and 4. And what does that give me on the top? The cube root of 4x plus 4 over a what? Regular 2. Cube root of 8, but regular 2. And that's your inverse. And again, what's supposed to happen on inverses with functions? If I plug like a 2 in there, what do I get? I plug a 2 in there, I get 15. So what should happen if I plug a 15 in here?
You should get a 2.
Let's check it out. Plug a 15 in there. 4 times 15 is 60. 60 plus 4 is 64. What's the cube root of 64? 4, and 4 over 2 is 2. You can see that switch. Right? And what do you think happens if I took this function and this inverse and said f of f inverse of x? What do you think happens if I do this?
It's going to be 2.
It would have to be 2. Because when I plug a 2 into here, I got a 15. And when I plug a 15 into here, I got a 2. And that's kind of what you'd be doing, right? Actually, this would be a little different. I'd be plugging 2 into this and getting a weird number, and then plugging a weird number into that and getting back to 2. But we know if they are inverses, which it's indicated that they are, that no matter what I plug in here, whether it's 2 or 12 or 120 or whatever, that would have to be true for an inverse function. You seeing it?
Yep.
What about this? Example 4.
First, find the inverse.
So find the inverse. So how would you do that for this?
X equals 3y.
Yeah, that's a y, so that becomes an x.
3y minus 1 over 2.
And then what would you do to make, that's technically the inverse relationship right there. But we want to make it pretty. So how do I pretty it up?
Well, multiply by 2.
Multiply both sides by 2 to get rid of that denominator.
X equals 3y minus 1. Add the 1.
Add a 1.
2x plus 1 and then divide by 3.
So when I divide by 3, how would you like to leave it? Are you going to say, now the y is your g inverse.
2x, so g inverse equals 2x plus 1.
So you could write 2x plus 1 over 3, or you could say 2/3 of an x plus a third if you wanted to make it look like a line. But you could write 2x plus 1 over 3 also. Now, here's something else about functions. and inverses that I want to talk about. Okay? Not every function has an inverse function. Okay? Hear that again. Not every function has an inverse. So let me just show you that clearly. And before I show that, I want to ask you about a rule, if you remember this. Did Miss Tyree or anybody ever teach you about how to check to see if something was a function? How? She said use the vertical line test, right? And the rule was if I drew a vertical line anywhere on the graph, it could only hit at most what?
1 point.
1 point. If it did hit 2, not a function. Like this red one right here, not a function. Now that doesn't mean it's bad. There's plenty of things that aren't functions. Circles aren't functions. We don't go, oh my gosh, no circles, right? So it's just not a function. So if I want to know what is the inverse function of this, here's a little check. You can see real quickly by this picture, if I reflect over that axis, I get this red graph, right? Now this red graph is clearly not a function. It looks like I should say, hey, this was the function, this was the inverse function. But if it doesn't pass the vertical line test, then how can it be a function? Are you with me on that? Is there any way that I could have looked at this and determined whether it had an inverse function before I actually sketched it?
Do a horizontal line.
It's called the horizontal line test. So the vertical line test, yes, this was a function. That's what the vertical line test checks. But the horizontal line test on a function checks to see if it has an inverse. And since I hit more than 1 point, it's not going to have an inverse. Because you can see right here, if this doesn't pass the horizontal, when I rotate it, I'm not going to pass the vertical. But it saves me the trouble. And you can look at these functions that we had before. This one that had an inverse, does it pass the vertical? Yes, so it is a function. Did it pass the horizontal? Yes, so it has an inverse. And if it passes both, there's a very special name to that. And the special name, I am guessing that I mentioned it, yes, is one-to-one. Now you learned a one-to-one property, and there may be some relationship there that I haven't put together in my head yet. But the one-to-one principle, when it comes to functions, it's easy to boil it down to just this. It passes both tests. If any function passes the horizontal and the vertical, that means that it is considered one-to-one. And what you'll notice about every one-to-one function has to just be increasing, or maybe just be decreasing, but it can't be increasing and decreasing, because these can pass all the horizontals and all the verticals I could possibly give them, right? But what happens if it increases and decreases? It may pass the horizontal, the verticals, but not those. Even if it increases and decreases just for a second, will not pass the horizontal. Are you with me? So for a function to have an inverse, it has to be one-to-one. To have an inverse function, it has to be one-to-one, which means it has to pass both of these tests. And that often is one of the easier questions you'll see. You just have to remember that definition. So you might want to make a point to kind of know what we're talking about here, because it probably will pop up on a test. Now, I have a question for you. You've learned about this equation, all right? What does it look like? We haven't done a lot with those. What does it look like? Y equals x squared? It's a parabola. And if you plotted enough points, plug in a 0, I get a 0. Plug in a 1, I get a 1. Plug in a negative 1, I get a 1. Plug in a 2, I get a 4. Negative 2, I get a 4. Plug in a 3, I get a 9. Negative 3, I get a 9. And slowly and surely you see a parabola. You're going to notice eventually in this course and the next course that anytime your highest power is even, whether it's y equals x squared, y equals x to the 4th, y equals x to the 6th, the arms of the graph always go, not necessarily up, but always go in the same direction. And if you're going up to the right and up to the left, then what are you eventually doing? You are decreasing and what? At some point, increasing. And if that's the case, are you ever gonna pass a horizontal line test? No. Well, if you sink that in your head, what that means is if your highest power is even, which all of these were, it's never gonna pass the horizontal because those parts going up are eventually gonna hit, and sometimes it hits a whole lot more, right? But I know it's gonna hit at least 2 points and fail the horizontal. And if it fails the horizontal, am I going to be able to find an inverse? I am not. And every year I give stuff like this. I give problems like this and say determine the inverse. My hope is you'll go, wait a minute, that is even. There is no inverse to this. If I give you this thing and say find the inverse, wait a minute, find the inverse? That is even. There is no inverse for that. Now, if you didn't catch that, and you went through the trouble of changing that to X and changing that to Y, look what happens in your process. You add the 2, you divide by the 3, and what would your last step be? 4th root? What happens when I 4th root both sides? Plus or minus? What does that plus or minus mean? That means that for every X value I plug in, I get what? 2 Y values. Isn't that not the definition of an inverse? If I plug in X and I get 2 Y values, it's going to fail the vertical. So the inverse failed the vertical. But hopefully you will just go, that's an even power in the function. This has no inverse. Like on this one, I say sketch it. Sketch the inverse. I'm hoping you look at that and go, has no inverse. I'm hoping you look at this and go, has no inverse. And I'm hoping you look at this and go, okay, that does pass the horizontal and the vertical. It does have an inverse. And to find it, what are you going to do? Find a whole bunch of points on this thing and sketch all of those ABs. I'm going to sketch all of the BAs that go with them.
What would we write if we what would our answer be if you said determine the inverse? We would just write no inverse? Not possible.
Yeah, or I can't do it. It's not possible. Yeah, literally answer the question. If I say find the inverse and then that is one, you can say there isn't one. There's no inverse. Can't do it. Possible, I don't know, whatever. Yeah, but probably no inverse would be pretty clear. Okay, now what if I asked you this? Determine if F and G are inverses. Now there are myriad ways for you to do this. So let's think. Determine if they're inverses. Somebody give me one way that pops in your head. If they're inverses, how would you prove it? Come on, some of you are waiting for somebody else to speak. Literally, engage your brain. Think about all you know is inverses. If they're inverses, how would you prove it?
Well, you do one of the tests, or you check for that even exponent.
Yeah, we've got odd exponents, so it's possible.
If you plugged in a number as X into one of the equations and got that number, and you can plug the number that you got into the other equation.
Does that make sense? What he's saying? He's saying if they're inverses, then like a 2 blah in here would be the same thing as a blah 2 in here. Like for instance, if I plugged a 2 into this, I get what? 8 times 4 is 32. 32 minus 12 is 20. Then a 20 in here should give me a 2. Let's check it. A fourth of 20 is 5. 5 plus 3 is 8. Cubed of 8 is 2. Now here's the problem with this. I've actually had this happen a number of times to people. They just were the most unlucky people on the planet, and they just happened to pick a number that when they plugged it in there, that was true. But if they'd have picked any other number in the universe, it wouldn't have been true. So it's risky, but that is a check that you could do. Now what's less risky is to maybe check a couple more points. But is that really proving it? Or is that just kind of guessing and checking?
That's good.
What would be a proof?
Could you switch the
How do I plug every X value in this. How do I do that?
X equals any real number.
Like, think about it. If I plug an X into
Oh,
this,
is it?
what is my Y? If
It's
I plug,
greater than 0.
hold on for a second. If I plug an X into this function, what is my Y?
4x.
4x cubed minus 12, right? That's the function. And then if I plug a what? If I plug a 4x cubed minus 12 into this, I should get back to x. What does it feel like I'm doing there?
Substitution.
What am I plugging technically into this?
You're,
Other equation.
It's a composite
Oh
function.
my goodness.
I'm checking g of f of x to see if it's x. That was our definition of an inverse, right? So to check to see if they're inverses, check these definitions. All right? I went g of f of x, but I can check f of g of x, and I'm supposed to get x both times. That is option 1, that it's a real proof. So what's g of x? This ugly thing. Plug that ugly thing in there to the f. So 4 ugly thing cubed minus 12. Take that ugly thing, plug it in here. Now what's the first thing you do to simplify? Cube roots go away, leaving me 4 times the 1/4 x plus 3. Next thing you would do,
Distribute that forward.
distribute, and you get x plus 3, x plus 12 minus 12, and then,
You just got it.
oh, f of g of x is x. That's a proof. Now technically I would need to go through the other one as well, but now, isn't this another one? That's the best one, because you literally are using the definition of an inverse. If that is true, then it's a definition of an inverse. So I just verified. Now again, a perfect verification would also go back and check g of f of x. Now, what about this? Isn't it possible, if they're inverses, couldn't I just find the inverse of this and see if it is that? So I could say, hey, switch that to an x, switch that to a y. Now here's the only downfall on this. And when I'm resolving, I go, all right, is the cube root of x plus 12 over 4 the same thing as that? Ooh, doesn't look the same. Oh, wait a second. If I clean it up maybe a little bit, then it is. Are you with me? So if I take that, I could technically write that as 1/4 x plus 3. So yeah, it looks like they are matched. And you could have used the other function too. Y'all seeing that? But the whole plugging a number in, again, that's true for that value, but that's really not a proof. A proof is to show it for everyone, and we just literally use the equation that stands for every x value that goes in. All right, we got 4 more minutes. So,
It's 30 seconds.
yeah, anyway, make sure you do your homework on this. Hey, I have a quick review. I gotta be honest with you guys, if I were you, I'd go through that quick review of composites. Just to make sure you're in a good place. Let me make sure that that's on school review. Okay, it is not, so I'll try to do that and get it posted. It may not be posted till the end of the day or whatever, but good chance you're not gonna look at it. If I were you, I would do that, make sure that you're in good shape on it, and I'd do the homework too, but technically, I'm not taking it up. You might even save that for a good review for your test, but anyway, threw that out there. I'm just a little short on time. All right. Anybody got anything good going on this weekend? Good? Some cash?
Are you a big baseball fan? Is that what you're?
I'm not like Homer, like I don't like religiously follow the Braves or anything, but I love playing baseball when I was a kid. What do you guys?
You like Auburn baseball?
I kept up with it more, like when they have good teams, like they're supposed to have a really good team coming up this year.
Yeah, one of my like really good friends, her dad's the opera coach.
Oh, really? He's a good guy, I like that their coach right now.
Yeah, he's really shy.
Yeah?
Yeah, he's really sweet.
Yeah, he's very calm and
Yeah.
very stoic in his interviews and stuff like that, but evidently he's a great pitching coach and,
His house is ginormous.
oh yeah?
It's huge.
Live out in Moore's Mill,
What'd you say?
does he live in Moore's Mill in Auburn?
Mm-hmm. I went there like 2 weekends ago and spent the night, and it's ginormous.
Yeah, all those coaches are out there.
Yeah.
It's a really nice area.
He's like best friends with like Gus and like. It's really
Yeah.
Speaking of that, they just released the basketball schedule.
Yeah? Or basketball school then?
Arkansas, Texas A&M, Ole Miss, Bama, Georgia, Kentucky, and Arkansas, and South Carolina, and Missouri.
I think we're gonna be pretty good.
Oh,
They have us ranked at like 80.
Yeah, we
80th.
80th, yeah.
They had us ranked for the last year too.
80th? That's horrible.
Yeah. I think we're gonna be pretty decent. We have some really talented guys that just not experienced. It's 4-star, 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 all the way down. And then our point guard is a freshman, but he's a 5-star freshman.
We got the number 5 recruit coming in next year too.
That dude's dirty. And we got some 7-footer out of
Oh,
Hawaii.
yeah, I saw that.
It's only currently a junior,
Yeah,
but I'm hoping he reclassifies.
yeah,
And he'll be probably a top 30 guy.
yeah. He's huge.
Yeah, our team right now, we're gonna be really long.
Yeah.
I mean, our point guard's short, like 5'11" or whatever. I mean, we
That's top
have
5 guys.
speed, skill everywhere on the floor.
That's top 5 guys. Like 6'11". He's coming in next year.
Yeah, yeah, he is.
He can shoot.
He's nasty. Yeah, it will be a really tough matchup because he can run, shoot, finish. So,
How are you?
all right. Probably didn't need that last 5 minutes of blank wall.